Thank you for the talk. Next speaker is Piotr Mormul, and the topic of his speech is non-simple, strongly nilpotent distribution germs. Please, Piotr.
So thank you for giving me this possibility. And first of all, I strongly wish that we meet in future in Odessa in person, that this series of conferences will continue in more quiet, peaceful conditions. I strongly wish to all of us this. So I keep advertising notion of strong nilpotency of distributions. This will be defined in a moment as opposed to weak nilpotency or local nilpotentizability, as you see on this initial slide. I have only 5 slides. The talk is short because I'm going to announce just one result, an answer to an old question in so-called non-holonomic analysis. What is non-holonomic analysis? It's analysis on manifolds endowed with a completely non-holonomic distribution, geometric distribution, subbundle in tangent bundle, generating all directions, all dimensions upon taking more and more Lie brackets. So completely non-holonomic distribution on a manifold, giving rise to example of non-holonomic analysis. So local nilpotentizability, as you see on this slide, this is an old question, old notion used strongly by geometric control theorists and quite important for solving problems in control theory, because when one has such information that a given distribution has a local basis of sections, set of vector fields spanning that distribution, such vector fields that span nilpotent Lie algebra over numbers, over reals, not functions. So this is important notion, local nilpotentizability, that I'm going to rephrase as weak nilpotency. So for a moment, let me recall, just to give you an example, Hector Sussman, quite an important person in control theory, geometric control theory, and not only. He kept asking about newer and newer classes of distributions having that property, having local basis of sections span generating nilpotent Lie algebras. For instance, a long time ago, 26 years ago, he asked if well-known Goursat distributions are locally nilpotentizable in this sense. So it was not so easy to answer his question only 2 years later. And I continued. There is a much wider and also interesting class of objects, so-called distribution spanning special multiflags, but I'm not going to talk about them right now. So they are also weakly nilpotent, or in this new terminology in a moment. But what is important for my presentation is the presence or absence of local invariance, of numerical invariance in problems of local classification of distributions. So sticking for a moment to Goursat objects that are quite classical and investigated since the end of 19th century. So it was not Goursat who invented them, but the general meta principle of Arnold applies, that objects are named not after the original inventors. Yes. So Goursat just popularized, made advertisement of objects investigated by Elie Cartan, by von Weber, by Engel, classical Engel. So it appears that in Goursat, in local classification of Goursat, they are moduli. They are moduli. And also in those special multiflags, they are also moduli. So let's stick to Arnold terminology. Within the world of Goursat, or within the world of special multiflags, there are objects that are non-simple. This is singularity theory terminology, non-simplicity, that is to say, existence of moduli, of numerical invariants in local classification. So in prescribed classes of weakly nilpotent or nilpotentizable structures, distributions, the moduli are naturally existing. Okay, but and they could exist in number 1, 2, or 3, or in fact in Gursa, the number of moduli is unbounded because Gursa distributions exist on manifolds of arbitrary dimension. So so-called length of the Gursa flag could be unbounded, and then the number of moduli is unbounded. But my talk is not about that kind of moduli. So let's now stick to this notion of weak nilpotency. Instead of local nilpotentizability, I prefer to use the name weak nilpotency as opposed to strong nilpotency. The talk is about strong nilpotency, so my attempt, one more attempt at advertising strong nilpotency. So what is strong nilpotency of distributions? You see the definition here. The problem is that for completely non-colonial distribution, one can compute or obtain its nilpotent approximation. This is absolutely classical object, essential in differential geometry, in geometric control theory. So whenever the distribution is locally, is equivalent, it's a completely local notion, nilpotent approximation. So when the germ of a distribution is equivalent to its nilpotent approximation around a point, then such a germ, such a distribution locally around that point is called strongly nilpotent. So this is really essential notion. And of course, strong nilpotency implies weak, but not the other way around, not at all. The first example that there exist weak nilpotent distributions and not being strong, that first example was constructed during a conference in Trieste organized by Professor Agrachov, who himself was surprised by the first example produced during that conference by myself. Let me briefly show you that example, but not dwelling on it. It is in dimension 6, it is a Gursa object. In Gursa world, one uses so-called compare-Ruiz coordinates. So you see the object basically, but of course it's no time to dwell too long on it. It is weakly nilpotent, that is to say you just have the couple of local generators that generate nilpotent Lie algebra. So Lie algebra over numbers, over reals, generated by these two vector fields, these two generators, is nilpotent of nilpotency order 7, and it is not strongly nilpotent because applying classical algorithm, going back to Belaish, also to Agrachov, Sarychev, Gamkrelidze even. So there is such a paper, Gamkrelidze, Agrachov, Sarychev from the end of the 80s. They started to compute nilpotent approximations. So the nilpotent approximation of this very first example is not equivalent to the initial germ. And why this nilpotent approximation is strongly nilpotent? This is general. All nilpotent approximations are strongly nilpotent because when one applies this so-called functor of nilpotent approximation to the thing being already, then one gets nothing more. So it is automatically. So nilpotent approximations are strongly, but that the initial example is not equivalent. It is a quick argument, but I'm not going to present it. But this is really a prehistory starting point. We are for a moment in the year 2000 at that interesting conference in Trieste in June 2000. So just for recollection, there are non-simple weakly nilpotent. This I stressed sufficiently. But bad news is that those moduli, those invariant parameters omnipresent in Gursa or special multiflex, are not descending to the level of nilpotent approximations. So that was the old question of Professor Agachov, whether the moduli found in Gursar, whether they descend to the level of nilpotent approximations. And not all existing examples show that they disappear. And conjecturally, all of them, all moduli of Gursar, and possibly also special moduli, disappear when passing down to the nilpotent approximations. But this is not yet proof, this is conjecture, but all examples confirm that conjecture. So while my objective or attempts at answering also old question was whether strong nilpotency admit non-simple objects, but non-simple in Arnold's sense within the objects being strongly nilpotent. Okay, so this is the objective of my presentation. So let me formulate this question. Do there exist non-simple strongly nilpotent? Meaning non-simple in Arnold says, I'm stressing, not forgetting about previous weak nilpotency, just within the class of strongly nilpotent. This is not well investigated class yet, but the question is old, whether invariant moduli, invariant parameters are possible inside the world of strongly nilpotent distribution germs. So it was a long time and it was a long way to try to answer that question. The answer is in the affirmative. And in fact, that was during series of singularity theory conferences in Japan in autumn and beginning of winter 2022 that eventually I arrived at an answer, positive answer. And the objective is to present such an example. So example of one parameter family of strongly nilpotent and pairwise non-equivalent rank 2 distributions. So let me dwell for a moment on that example. It is relatively short, as you see, but the way to arrive at it was really long, several years, and several unsuccessful attempts. Of course, no way to explain the trajectory leading to that example, but let's focus on example itself. So it is rank 2, you have two vector field generators. The dimension, the underlying dimension is 7. So the components, the vector fields are written vertically and components are numbered as you see here. So 7 variables, but not all Z1 up to Z7, and not all of them are actively used in the description. You see the example actively uses Z1, Z2, and Z3 only, but of course it uses all 7 directions. And in non-holonomic analysis, it is a classical object, so weights are being associated to a completely non-holonomic distribution germ. Or equivalently speaking, such an object has its small growth vector. So the sequence of linear dimensions of the Lie flag. So one starts from rank 2 and one adds more and more Lie brackets, each time multiplying with initial generators only. So this is Lie flag, not to be confused with big or derived flag. That is another story not to be recalled today. So small growth vector, the sequence of linear dimensions of the Lie flag at a given point, at the reference point, or equivalently speaking, the sequence of weights. So the weights are written here, you see them. And this example, the family of examples, it is family, you see this parameter. The C is a real parameter. And the statement proved recently is that any two such distribution germs with two different values of this parameter C, so say C and tilde C, they are not equivalent. They are not equivalent. But let me say, yes, thank you. Let me say something more about this example yet. So maybe how to try to prove that the two different values of C are not equivalent. One tries to write down conjugating diffeomorphism. In fact, it is standard thing. It is this equation, and one carefully expand the component-wise and obtains a sequence of equations for coefficients of this hypothetically conjugating diffeomorphism. In fact, such a diffeomorphism doesn't exist. It exists only when C is equal to tilde C. But for a moment, we suppose its existence, we get a huge number of equations for coefficients because all objects are homogeneous with respect to the weights I indicated previously. So it is no way, the only implication is that C must be equal C tilde. So really, we have non-equivalent family, so non-simple. Modality is at least one. Modality in Arnold terminology, control singularity theory. And why all these objects are strongly nilpotent? Because they are automatically equal, even equal to the nilpotent approximations. Just for a second, simply these coordinates, these z coordinates are already adapted in terminology of differential geometry. They are already adapted, and these are just the quasi jet -1 object. So it is just equal to its nilpotent approximation. So just to finish, I want to say that skipping the algebra description, because it is just technical thing, I'm skipping it, but I would like to advertise some notion coming from this paper. So Agrachov and Marigo, quite an old paper already, but closely related to the objects I'm presenting. So they use notion of bidimension of Lie algebra. So the dimension of the -1 component, in this case 2, and the dimension of the full Lie algebra. So 2, 10 is by dimension of this family of examples. And my family of examples generalizes. So this is unimodal, as I just told. And to get bimodal family all the time of strongly nilpotent. So we stay within the world of strongly nilpotent. To get bimodal, one extends the previous example. Let me just show to finish. Let me show this. So now I'm situating myself in underlying dimension 8. So the 8 components. So again, rank 2 vector field generators, but 2 parameters, 2 real parameters, C and D. You see C, previous C, and there is just a new parameter D. And again, the 2 such objects are just equivalent, locally equivalent, only when C is the same as tilde C and D, the same as tilde D. And what about bidimension? It is 2, 12 this time, and this sequence of examples, families of examples, generalizes in underlying dimension 9. One could have 3 modal, etc. Just to finish, last statement. The associated Lie algebras, yes, because we are talking about nilpotent approximations, but parallel language is Lie algebra, so they are so-called Carnot algebras. That is to say, graded nilpotent. The gradation is clear from the weights I was presenting. So the graded homogeneous components have been displayed already. And those algebras are also pairwise non-isomorphic. It is the same. It is equivalent to say that the objects constructed are not locally equivalent because they are quasi-homogeneous. So in the terminology of Agrachov-Marigo, these algebras are non-rigid. So in fact, my result is a comment. It's a kind of comment to the theory being developed by Professor Agrachov with his collaborators. So thank you for your attention. Thank you.